Okay, let's just dive right in. Have you ever been in a physics class? You see some weird symbol like epsilon zero, and your teacher just says, hey, just don't worry about what it means. Just plug it into the formula. Well, today, we're going to break that rule. We are unlocking the meaning behind one of the most fundamental, yet weirdly overlooked constants in all of physics. Permittivity. And believe me, it is so much cooler than it sounds. So this whole thing kicks off with a question from a curious 17-year-old on Reddit. Gremlin Star 07. Their teacher literally told them it wasn't required to know the meaning of the permittivity of free space, epsilon naught. But they got curious. And that little spark of curiosity, that's exactly what we're going to be exploring. You know, this is what I love to call a forbidden physics question. It's that little detail you're told to just gloss over for the test, but it's actually the key. It's the thing that unlocks a way deeper understanding of how the universe is wired together. So yeah, let's get into it. Now, before we even think about looking at an equation, we're going to build some intuition. We need to get a feel for this thing. And what's a better way to do that than with a good analogy? So picture this. You're in a very, very noisy room. The whole idea here really boils down to resistance. But how on earth are you supposed to visualize that? I mean, how can a material resist something as invisible and abstract as an electric field? How could you even begin to picture that? Well, here is how one Redditor brilliantly explained it. Imagine you're at a daycare, and you are desperately trying to get the carer's attention for some yogurt. Your voice? That's the electric field. The room, just full of screaming kids? That's the material, the medium. So, what's permittivity? It's literally how much those other kids get in the way. A material with high permittivity is like a super loud, chaotic room. It resists your voice. A vacuum, though, with the lowest permittivity, that's a perfectly quiet room. Your message gets through, no problem. And here's another way to think about the same idea, just from a slightly different angle. Another person suggested this. Imagine you're pushing a little paper boat across some water. In clean, clear water, it glides pretty easily, right? But now, try to push it through thick, muddy water. There's way more resistance, the boat goes slower. That muddy water has a higher permittivity to the boat's motion. It's all about how much the medium pushes back. Okay, so we've got the feel for it, right? The analogies are locked in, a noisy room, muddy water, we get it. Now it's time to connect that feeling to the formal physics, to bridge that gap between the intuition and the actual equations. And here we go, the textbook definition. Permittivity, a measure of how an electric field affects and is affected by a dielectric medium. Okay, fine, but look at that last part. It describes the medium's resistance to the formation of an electric field. There it is. That's our noisy room. That's our muddy water. The formal physics lines up perfectly with what we already feel. Now, this is a super important point, something the original poster, Gremlin Star, actually figured out on their own. That constant we always see, epsilon zero, that's specifically for the permittivity of a vacuum, of empty space. But permittivity in general is not some universal number etched in stone. No, it's a property of the material itself. Water, plastic, air, they all have their own unique permittivity values. But why is it even a constant in the first place? This is the absolute key, the real aha moment. As user Intrepid Pilot 2552 put it so perfectly, the constant exists because the relationship between a charge and the field it creates is linear. It's not some crazy complicated curve. It's a simple, straight line, y equals mx relationship. And permittivity? It's just m. It's the slope. It's the constant of proportionality that connects the two. And here it is, right in the wild. Look at this formula for the electric field E between capacitor plates. On top, you've got sigma, the charge density. And on the bottom, there's our friend epsilon naught, tweaked by K, the factor for whatever material is in there. This number is the direct link between how much charge you have and how strong the resulting field is going to be. All right, we've gone from a curious question to some fun analogies to the actual physics. So now for the payoff. Let's see how understanding this stuff isn't just for a test. It's how you actually solve problems. It's time to put permittivity to work. So check out this first setup, which comes from one of the problems in our source material. You've got a charged sphere, and it's sitting inside a hollow metal shell. There's a certain voltage between them. So the big question is, what happens to that voltage if we just dump a bunch of extra charge onto the outside of the outer shell? Okay, so look at the left, that's our starting point. You've got a positive charge on the little sphere inside, which pulls some negative charge to the inner surface of the big shell. Now look at the right. We've just added a ton of negative charge to the outside. But notice where it stays. It's all on the outside. it doesn't seem to care about what's happening in that gap. Why is that? Because the electric field inside that empty space only depends on the charge that's enclosed inside it. That's a fundamental rule of electrostatics, and it's directly tied to how permittivity governs those fields. So all that charge on the outside, it doesn't change the field on the inside one bit. And so the potential difference, the voltage, stays exactly the same. See? It's a conceptual thing, not just a bunch of math. Okay, let's try a totally different problem. This one's way more practical, more of an engineering question. We've got a capacitor, and we know its size, we know its capacitance. What we need to figure out is the property of the special material that's tucked inside it. Its dielectric constant, K. And guess what? To do that, we absolutely have to use the permittivity constant, epsilon 0. So you take the formula for capacitance, you rearrange it, you plug in all the values you know, and you use our trusty constant for the permittivity of free space. And what do you get? A concrete number. The dielectric constant for this material is 8.5. Now think about that for a second. We just used a fundamental constant of empty space to precisely measure a property of a real physical object. How cool is that? All right, so let's zoom back out. We started with what seemed like a simple, almost trivial question about some constant in a textbook. But it turns out this one number is kind of like the linchpin. It's the constant that connects everything in the world of electrostatics. So let's just recap the whole thing. What is permittivity? Well, at its core, it's a measure of resistance. It's our noisy room. It's the constant that proves the link between charge and field is beautifully simple and linear. It's a real-world property of actual stuff that we use to build things like capacitors. And, as we just saw, getting your head around it is the absolute key to solving some really tricky physics problems. And that brings us to one last final thought. We've established that permittivity is all about how an electric field moves or propagates through a medium. So here's a little something to chew on. If this constant describes how electric fields travel, what might it have to do with the speed of something else that travels as an electromagnetic wave? Something like, say, the speed of light? The answer is absolutely fascinating, and it's the perfect reason to never, ever stop asking those forbidden questions. Stay curious.